Welcome back to our ongoing discussion on basic trigonometric equations. Last time we started looking at what we would get for general solutions to a generic equation. And today, or whatever day you choose to watch this, now we will be looking at specific equations. So kind of have some samples, some examples of equations to solve and showing how to incorporate the general solutions we found last time into our solutions of these equations. So here's where we left off. If we had some equation, we had to use the arc sign to get some value, recognizing that that will only give you something in the first or fourth quadrants. You would have to get the other solution out of the second or third quadrants respectively by taking negative theta instead of the theta you found and adding that to pi. So we went from theta plus 2k pi to negative theta plus some odd multiple of pi. Right? 2k is even, 2k plus 1 is odd, and k is just any and every integer. With the case of arc cosine, since that only gives you values in the first and second quadrants, you would have to get negative theta to get into the third or fourth quadrants. And so we have either theta plus 2k pi and negative theta plus 2k pi. And the 2 pi business comes about because we have a function that's periodic with period 2 pi. And then lastly, arctangent. That's kind of nice because that gives you something in the first quadrant which can be sent down to the third quadrant by adding pi, and something in the second quadrant, second and fourth quadrant, which gets sent up to the second quadrant by adding pi as well. So whatever you get from arctangent, your general solution is just that plus k pi. And we'll be exploiting that, using that in all of the examples to come. So let's get going here. The first example, we'll start simple here, we'll start small. Find all the solutions to the equation 2 sine x plus 1 equals to 0. And I see a sign, I want to undo the sign, but I can't just do the arc sign right now, not as it is, because I would have to take that of both sides, and that would tell me that the arc sign of 2 sine x plus 1 is equal to the arc sign of 0, and well, that's not really a thing I can do, right? I can't distribute the arc sign across an expression. In the same way I can't distribute sines, so too can I not distribute its inverse arc sign. So this is not a thing I can do. Instead, what I have to do is first solve for sine x by moving the 1 over, dividing the 2, so I have sine x equal to negative a half, and I can undo sine by applying arc sign directly to it. So the arc sign of negative a half you'll find to be negative pi over 6, right? That's the value between plus or minus pi over 2, having the sign of that number equaling negative a half, and that's all you would get from a calculator. And that's not nearly all the solutions. The other way you would get, the other one that would work between 0 and 2 pi would be adding pi over 6, right? Or subtracting negative pi over 6 to pi, giving you 7 pi over 6. So in all of your solutions should look like 7 pi over 6 plus 2k pi and 11 pi over 6 plus 2k pi. Right, the 7 pi over 6 came from our alternate form, and the 11 pi over 6 came about because that's coterminal with negative pi over 6, and I just felt like stylistically I wanted to do that. Not that I had to, but I could. You could just as well have said x had got to be negative pi over 6 plus 2k pi. That's also true. Alright, so far so good. Now here's an example which is almost solved for us, right? Find when secant of x is equal to 2. And you could do this just by looking at the unit circle and saying, okay, when is the reciprocal of cosine 2? That means when is cosine a half? And that's going to happen at pi over 3 and at negative pi over 3. So that would be one approach. If you want to do it algebraically, if you want to solve for it directly using algebra techniques, you would have to do a little bit of what we did here. Right, we would write secant as 1 over cosine, and then I multiply both sides by cosine, which I can do, by the way, because since secant is undefined when x is pi over 2, negative pi over 2, those sort of things, undefined is never going to equal 2. So I'm going to multiply it by cosine, where cosine is never 0, because cosine equaling 0 does not give me any extraneous solutions. And so after some manipulation I get to cosine x equals a half. Well, I can do the arc cosine of that to both sides, find out from my calculator or from the way that arc cosine is defined, that pi over 3 is what I need, right? That is what arc cosine would give me for a half. So that's a solution. But also, since we use arc cosine, I know that also in the fourth quadrant, negative pi over 3 has cosine of a half, so negative pi over 3 is also a solution. And so if I want to write the general solutions, if I want to write all the possible solutions, I would have pi over 3 plus 2k pi, and negative pi over 3 plus 2k pi. Now that's not to say you couldn't say 5 pi over 3 plus 2k pi, right? That's coterminal with negative pi over 3. It's just really a matter of taste. A lot of people, and your author is included in this bunch, likes to have the value that you have here before you add the 2k pi to be between 0 and 2 pi. I don't know why they do that, but they do that. So here we are. All right, moving right along. Here's where things get a little more interesting. Find all solutions to the equation where I've got 4 cosine theta times sine theta equaling plus 3 cosine theta all equal to 0. And I don't have some inverse trig function that undoes simultaneously sine and cosine, right? There's no arc sine cosine function. So I don't have a direct means of solving for this. And some of you might be thinking, okay, well, I've got 4 cosine sine. That's 2 sine 2 theta, right? And you wouldn't be wrong. But I would still have to add 3 cosine theta to that. I would have to find a way to combine 2 sine 2 theta with 3 cosine theta, and I'm not sure how to do that, to be honest with you. So that might be, while true, might be taking us further away from what we want. So what we should probably do instead is some more algebra techniques, right? This is an equation. Even though it's got trigonometric functions in it, we can still use algebra techniques before we use our trigonometric techniques, right? These have common factors. There's a cosine theta common to both. So what I can do is I can factor out cosine theta. And I know some of you are a little upset about this because that looks a lot like I had factored out cosine without this theta, right? But this is okay. This is okay, right? Cosine of 4 sine theta plus 3. If this were the argument of my cosine, then I would be in trouble. I could not distribute cosine across its argument. But the argument here of cosine is theta. This is 4 times cosine theta times sine theta. 3 times cosine theta. So what I'm factoring out is cosine with its argument. I'm factoring out cosine theta, and I can do that. That's fine. Because I can then distribute cosine with its argument back across. That's okay. That's algebra. That's good. That's legit. So, having done that, recognizing I've got 2 things that multiply together to equal 0, that means that's going to be true if either factor is 0. So again, we bring in some algebra techniques. We set either side equal to 0, and I've got, well, cosine has to be 0. So either I've got pi over 2 plus 2k pi, because cosine of pi over 2 is 0, but so too is cosine of negative pi over 2 plus 2k pi. And actually there's a nice way of writing this if you're a stylistic kind of person, and I'll let you try and parse out what that is here after a moment here, because I also want to say, well, for the other factor, right, 4 sine theta plus 3 equaling 0, that's when sine of theta is equal to negative 3 over 4, which is not a nice value. I have to do an arc sine here, and that's going to give me negative 0.848 radians, which is about probably some number of degrees. I don't want to work that out right now. And also about 4 radians plus 2k pi. And that's both your solutions there. So again, is there a nice way to sum up both of these together? Let me know. And we'll do one more example. Alright, last guy here. I want to find all solutions to tangent squared x plus 4 tangent x plus 3 equaling 0. I don't have a nice thing for this, right? I could do a power reduction formula, but that would give me 1 plus cosine 2x, 1 minus cosine 2x, or is it minus over plus? I forget. But that would be that, and then I have tangent still, and I have a 3 here. Doing that would get me no closer to a solution. So not doing trigonometric techniques, doing algebra techniques first, let's factor this. I've got something squared plus 4 something plus 3. Give me two numbers that multiply to 3 and add to 4. Positive 3, positive 1. This expression on the left factors to this expression, tangent x plus 1, tangent x plus 3. And tangent x plus 1 is true whenever you're looking at negative pi over 4 as x, or in other words, 3 pi over 4 plus k pi. And this is true whenever tangent is negative 3, which is not a nice value, so I have to approximate it. And that's going to give me approximately negative 1.249 plus k pi. You could technically add pi to this, get another positive decimal if that's what you want, and that would work as well. These are your solutions. Alright, well, I've got just a little more I want to say, and that is this right? Is this right? Hang on. I actually graphed this thing. This is what this left-hand expression looks like. 4 cosine theta sine theta plus 3 cosine theta. I know I used x here, sue me. And yeah, this actually is your solutions. Pi over 2. 3 pi over 2. 5 pi over 2. Negative pi over 2. Negative 3 pi over 2. Negative 5 pi over 2. So there's your pi over 2 plus k pi. Sorry, pi over 2 plus, yeah, k pi. Sorry, I was right. So there's those. Here's your 3.99 plus 2k pi. Oh, not that one. And here is your negative 0.848 plus 2k pi. And that's got, altogether, all your solutions. Exciting, I know. Clicking buttons is fun. Alright, well that's enough of this video. We will pick up with this some other time. This is the last for 7.4, the basic trigonometric equations. You'll be using algebra techniques when you can't just solve directly for your sine or cosine or tangent function. And then you'll apply the appropriate inverse trig function. And then you'll apply the appropriate methods to get all the solutions from what you get from your inverse trig function. And that's all we got to do. Simple as that. Maybe not easy as that, but simple as that. And so I will see you up ahead. Have a good one.